Welcome to the final lecture of this series. So today we are going to prove the undertake theorem about the classification of Abelian varieties over finite fields. And before we do this, we are going to recall some of the results we will need in non-commutative algebra, and then we will use those for the proof in the second part of the lecture. So I'm going to start by recalling some result about simple algebras, and then we will go from there. So we are going to fix a field K. Okay, a field. And then, so the first definition is a recollection. So that's a central simple algebra. So a central simple algebra so algebra over K is a K algebra. In this case, I'm going to always assume that the finite dimensional K algebra A, which satisfy the following condition. So the first condition, okay, I just repeated basically. So finite dimensional, and then you want K to be the center of, so K is the center of A. And then you want A to be simple, which we saw before. And this means that the only two-sided ideal, so the only two-sided ideal in A are the trivial ideals and A itself. So that's what we mean by a central simple algebra. And if in addition, let's say in addition, we know that A is a division algebra. If in addition, A is a division algebra, is then we say that A is a division, a central division algebra. Okay, so these are more or less things that we saw already. Now we are going to give a theorem which gives a characterization of simple central algebra. So theorem. So let A be a finite dimensional. So we start with finite dimensional K algebra. And the theorem says the following. The following are equivalent. So the first one is that A is simple central. Central algebra, K algebra. And the second condition says that the following homomorphism is an isomorphism. So the canonical homomorphism. So remember when we of K algebras. So remember when we talked about semi-simple algebras, we defined what the opposite of an algebra was. So the canonical homomorphism that we're talking about is the following. So you take the tensor of A with itself, with opposite, and then you know that if you take any element, let's say A times A prime, there is a natural way to associate a homomorphism to it, which is by sending x to A times x times A prime. And so the second item say that this canonical homomorphism is an isomorphism. Okay. And the third statement says that there exists a field extension so L of K and some integer, so there exists, and N, an integer, such that when you tensor A by L over K, you get an isomorphism with the matrix algebra over L. So that's the third condition. And then the fourth condition, so this is a long list, but we are going to need them all. So if you take a separable, for any separable closure, so let's say we take a separable closure Ks of K, then there exists an integer n at least one, such that, so this condition is quite similar to what we just saw. It says that if I tensor A over K with this separable closure, I get an isomorphism with the matrix algebra over that separable closure. And then the fifth condition says that there exists a finite Galois extension L over K and an integer n greater or equal 1, such that, again, when you tensor A over K with that Galois extension, you get an isomorphism with the matrix algebra over L. And then the final condition is one that we saw before, which said that there exists a division algebra, a K division algebra, which I'm going to call D, and N, at least N an integer, such that when you take such that A would be isomorphic to the matrix algebra, the n by n matrix algebra with coefficient in D. So all of these statements are really not that hard to prove. So I'm going to say, see the notes. I gave a reference there for the proofs. But they are not really that hard to prove. But if you want to go on by yourself, I mean, you can do that. And we are going to derive a lot of consequences of this statement, and then those are going to be useful for us in the second part of this lecture. So the first corollary of what we just proved, the following. So if you let A be a central simple algebra, over an algebraically closed so it's a finite simple algebra over an algebraically closed field K. Then we see that A has to be the matrix algebra. Then A must be isomorphic to a matrix algebra for some n, at least one integer. So, I mean, you can see almost immediately which one of the conditions from this theorem would imply this statement. The second corollary is also easy to prove from the theorem. So let A be a central simple algebra over K. Then this says that then there's an integer n such that so this is basically saying that the dimension of A over K is a square. Okay. Again, this is fairly easy to prove from the using one of the equivalent condition in that we saw. The third corollary is the following. So if I let A be a simple central algebra, central simple K algebra, then if I let for any field extension L over K, if I extend the scalar from K to L, I get a simple central algebra. The central simple algebra over L. And then the second condition is it says that if I give myself another algebra, so let B be another central simple K algebra, then the tensor product of A and B over K is a central simple algebra as well. Okay, so all of these conditions are going to be really, really useful to us. So here is a consequence. Again, this is also still a consequence of the main theorem that we proved. So the following proposition. So we let A be a central simple algebra and L is a commutative K subalgebra. Of A. And the proposition says that the following are equivalent. The first one is saying that L is a maximal commutative subalgebra. So that's the first condition. The second condition says that L is a three is a free submodule of a 3K module whose dimension is of dimension LK, the degree of the field itself. And then the third condition says that if you look at the degree of A over its base field, that would be the square of the degree of L. So again, these are equivalent conditions to determine when a subalgebra is maximal commutative. I should say semi-simple. Okay. Okay. The other big result we are going to see, and then before is the next proposition, which would be used for the construction of the Brouwer group. And it says that we have the following. So let A be this central simple algebra. So these are two simple central K algebras. And then the proposition says that the following are equivalent. So the first one says that there exists an integer let's say t, at least one, such that when we take the tensor product of A with the opposite of B, we get an isomorphism with the matrix algebra over K of T by T. And The second condition says that there are integers R and S integers such that when I take A over K tensor with the R by R matrices with coefficient in K, I get an isomorphism with B tensor over K with M time with the S by S matrices over K. And the third condition is the following. It says that there exists a division algebra So you have a division algebra, D over K, and some integers, M, N, at least one, such that A is isomorphic to the M by M matrices with coefficient in D, and B is isomorphic to the N by N matrices with coefficient in D. So we have that these three conditions are equivalent. Again, all of those results are really easy to prove. If you accept the very first statement that I made, you would see that all of these are fairly easy to prove. And now we are going to make use of all of those results to define the Brouwer group and state some of the key properties of that group that we will need later. Okay. So, granted this proposition, we can define an equivalent relation on the set of this set of of element. Okay. Okay. So we are going to say that okay, so here is an equivalent relation. So you start with A and B, K algebras, and they are central simple, right? Then we say that A is equivalent to B if any of the equivalent condition of the previous propositions are satisfied. So if any of these condition is satisfied, then you say that the algebra A and B are equivalent. So it's very easy to see that this is an equivalent relation using this last proposition that we prove. So I'll leave it to you as an exercise. And now that we have this, we can define the Brouwer group. So the Brouwer group of the field F, or the Brouwer group of K is the set of equivalents equivalent classes of central simple algebras under this relation. The relation above. Okay. And what makes this even nicer is that, so we will denote, first let me say that we denote this by, so we denote it by Brouwer K. And the key thing is that it's even an Abelian group. It's an Abelian group. And so if you want the negative of a class, then it's just the class of the opposite algebra. And of course, the composition is basically, sorry, I forgot to say that. Yeah, okay, let me state things in the right order. So the composition law is what you expect it to be. So the composing the product of AB is simply the equivalent class of the tensor product. And you can show that it's actually an addition, it's an Abelian. And if you want the negative of a class, it's just the class, the opposite algebra. So these are the two things that define the Brouwer group. Okay. And so you see, another thing that I want to add is that, you see, if you take K prime over K, an extension, then you see that by extension of scalars, there is a homomorphism which go from the Brouwer group of K to the Brouwer group of K prime, right? Because remember, we proved that if you take a semi-simple algebra and you extend the scalar, you still get a semi-simple central algebra. And this map that you define that way is still, yeah. So that would still be a group homomorphism. So this is the map. Okay, the prime is not very visible. Okay. And now you can, so in fact, you can see that this is actually what we call a covariant. So the map which send a field. So the map which send a field to a Brouwer group is a covariant of, in fact, it's a covariant functor. Okay. And what you can show is that, and so the next fact that I want to show is that if you want the Brouwer group of a field K, what you can actually say that you can actually show that this is the disjoint union on all the Galois extension of the base field of the Breuer group of, and here, so the Breuer group of K prime over K, it's simply the kernel of this map that we just showed. So remember, we have the map which gives the extension of scalar. And I just take the kernel of this map, that's the Breuer group of the finite extension K prime over K. And then the Breuer group of my field K will be the union of all those finite, the Breuer group of those finite extension. And so here is one proposition, which is, again, I'm not going to prove it here for the lack of time, but the proof is given in the lecture note. So it says that if I let K prime over be a Galois extension, then there is an isomorphism between the Breuer group of this finite extension and the degree 2 cohomology group, which I'm going to gal of K prime over K with coefficient in the unit group. So for a shorthand, I'm going to denote this by in the future. So yeah, again, this is really not hard to prove. I gave the detail of this, the way you prove this in the lecture note. And as a consequence of this proposition, you get this key theorem that we are going to need. So the theorem says that if I let, yeah, I just saw some typos in my notes. So let Ks be a separable closure of K. Then there is an isomorphism from the Breuer group of K to the H2 of Fs over F with coefficient in Fs star. Okay. So this basically use the proposition that I just stated. So you basically show that. So in that proposition, we have this here that our Breuer group is this big union, and then using this, you just have to show that this union is compatible with the map on the restriction map on the side of the Galois H2, and then that's basically how you get this result. Okay. So the theorem that we are going to use is the description of the Breuer group in the case of the description of the Breuer group in the case of a local Archimedean field, and this is going to be very useful for us. And yeah. So for a local Archimedean field, so far the statements are for a very general number field. So now let's give ourselves a local, a non-Archimedean local field. Right. So in this case, you can define an isomorphism of between the Bryer group and a divisible group, Q over Z. And the way you do this is as follows. So if you let if you let K be the, so again here we are going to let Ks be a separable closure. This is a separable closure of K. And then by K and ramified, I mean the maximal and ramified extension or sub-extension of K contained in Ks, right? And then let K bar be the K bar and K be the residue field, of K of K and ramified and big K, right? And so the thing a fact that one can prove is the following: is that so this is the first fact, which is a fact from local class field, is that if I take the H2 of the unramified extension, with coefficient in K unramified, then this would be the same as the H2 of the separable closure. And then what one does from there is to use the fact that we have this normalized valuation. So now you recall that there is a normalized, that you have this normalized valuation taking values in Z. And if you recall this map, then it induces and the map is that we have would be H2 and K unramified over K unramified star, which in this case you can show that is isomorphic to H2 using the valuation map, evaluating the map. So this would be K unramified. Okay. So by evaluating, you get that if you take the K unramified over K with values in Z, you get an isomorphism. And then now using the connecting homomorphism of this, I'm going to, then you get that this would be isomorphic to H2, or sorry, H1 of the Galois group of the unramified extension over K value in this divisible group that I mentioned earlier. And then the key thing that you get from this statement is the following theorem, which is what we call the local invariant. So if you let K be a local non-Archimedean, okay, I think I put my adjective in the wrong order. Local non-Archimedean field. Then there is an isomorphism. Then the map, which we call inv K, going from the Brouwer group of K into this divisible group is an isomorphism, is a group isomorphism. Okay. So I'm going to give a proof of, I'm going to give a reference for the proof of this statement in the lecture note. And this isomorphism actually is quite explicit. You can work with this, you can compute this local invariant very easily. And I think there are several exercises in your problem set where this map, you have to evaluate this map. So it can be computed very explicitly. And the main result that we are going to need for today is the one that I'm going to state now. It's basically a classification, I guess it's both a classification result in some sense, and so it would be a classification result for, if you wish, division algebras, as we will see later. So here is the key theorem for today, or at least the first part of the lecture. So now we give ourselves a global field. So in our case, that would be a number field. And the theorem says the following, that there exists an exact sequence and the exact sequence is the following. So you start with your Brouwer group, and this will there will be an injection into the direct sum of Brouwer group over the local field. Okay. And then okay, let me, I'm running out of space. It's not that the thing is wrong, but I'm not very good at managing space. Okay, so the first map goes from the Brouwer group to the direct sum in all the places of the base field F, the Brouwer group of the local field at that place. You go to the Q over Z, and then 0. So this map here, I'm going to call it sigma, and then I'm going to tell you what this is. So so the first map is basically, so M is all the places of F. And so we have the second thing that I want to say, that we showed that if you have an extension of scalars, then you have a group homomorphism. So this is the extension of scalar. So this from K to its completion. And then the sigma basically is basically the sum of the invariant of each local field. So the key thing is that this is saying that only finitely many of those invariant will be non-zero. So this map, the mapping to Q mod Z makes sense. Okay. So this is really a very important theorem because, as I said, you can use the theorem to basically say that you have a classification of central simple division algebras, right? So that's basically the key thing that I want to say is, which is that so if so basically the theorem is saying the following. So if you let so if F is a global field and D is a division algebra. So this is an F division algebra. Then the key thing, so the first thing is that only finitely many of the invariant of D are non-zero. So that's very important. And then, of course, so only finitely many of those are non-zero. And then the second condition is that that set of local invariant determine D up to isomorphism. This is a really, really, really important result because it's something that you kind of use all the time when you work with division algebras. It's basically, you can compute in practice, you can often compute the local Brouwer invariant. And you know that each set of local Brouwer invariant would determine an algebra uniquely. Of course, we know that only finitely many of these invariant must be non-zero. So that's a key thing to keep in mind. Okay. So these are the results that I wanted to state in the first part. And in the second part of the lecture, we are going to use these results to prove in the proof of the undated theorem. So this is the end of the first part of the lecture. Thank you.